Yeah, I wanted to start by, let's see if I can change the introduction here and give you an idea about what solar energetic particles are. So it might be interesting to know that the solar energetic particles are uh, have a isotropic nature to them, and so they're a little bit disconnected or very much disconnected from the solar wind, and the fact that these energetic particles can impact the poles of the moon and the night side, and they can last for either several hours, potentially days. And they're composed of both primarily high energy electrons and protons. Um, Here we are going to study in the lab the solar energetic range of the electrons impacting a lunar simulant that could potentially lead to what's called dielectric breakdown. And the proposition of dielectric breakdown uh, has been studied by a series of papers over the last decade by our co-investigator Andrew Jordan, and looking at how this might be very uh, important for volatile migration, surface charging, and of course, space weathering. And so in a 2019 paper, he showed how, essentially the amount of dielectric breakdown could affect essentially the entire surface of the moon, up to 25% in the PSRs and 11% globally. Now, the regolith is very um, sort of primed for this breakdown to occur because of its low conductivity and, of course, the very low temperatures. And you can see from the plot on the right, we have the discharge time scale as a function of temperature, and you can see here in a matter of you know days, it could take that the regolith could charge up and would not dissipate this charge. So we set out to look at this experimentally, and here's a cartoon of our experiment. This is not at all to scale, but to give you an idea of sort of the different processes that's going on. So our camera is situated looking straight down on a small sample bed that's approximately an inch in diameter. And the electrons are actually magnetically bent down onto the sample and defocused. And we looked at three different energies, 30 keV, 50 keV, and 100 keV. And as the electrons impacted the surface, uh, we had a laser fan, so a laser that was spread out into a sheet that was on, and anything that crossed that laser fan, of course, would be detected by the camera, which is running typically at 100 frames per second. There was also a witness plate that was positioned above the sample to just see if what type of materials would be collected on the witness plate using SEM. Here at the top right, you can see this sample holder is connected to a helium cryostat, and the laser for these experiments were almost exactly a centimeter above the sample bed. Um, Here's a sort of an idea of the damage that was caused to the soil. We didn't compress the soil, but it was sort of pushed down lightly and smoothed. And then after irradiation from several runs at these high energy electrons, you can see that the soil looks very um, damaged. There's soil clods now that are exposed, and the soil is now present all throughout the sample holder. So the observations were shocking, to be honest. One of the very distinct things that we noticed was that um, we could simulate what essentially uh, has been termed like this dust hopping through this patch charge model if we just increase the flux. And so even though we had the high energy electrons, when we did it high flux, we noticed the grains essentially illuminating a single pixel, as you can see here on the left. Um, However, when we turn the flux down and use the high energy, we observe these large plumes, and these plumes were uh, very distinct. We never saw these single particles once we lowered the flux. It's almost counterintuitive in a way. The patch charge model turns off, and you start to get these very, very large plumes that are occurring, which are either disaggregations of dust grains or clusters of grains that are coming through the laser field. So because we took a lot of video and image data, we had to do a frame by frame analysis. In fact, it's more like a pixel by pixel analysis. And by doing this, one of our co-investigators, John Keller, produced some Python image analysis code to look at pixel frequency and intensity. And just one run would, you would have to analyze close to 300 million pixels. And we were able to do some statistics on these different plumes. And here, what you can see is that the on the x-axis is I'm sorry, on the y-axis is the frame, and up to like 10,000 frames if it's a little hard to see. And then the y, sorry, go back. The y and the x are just the pixels, and you can see at 30K you see these plumes. I've called them pancakes, but pancakes aren't really, you know, a good representation of what they are, because these are plumes that are coming up through the laser field. And as the energies increased, of course, the electrons are penetrating deeper into the grains, and these plumes increase to where um, each one of these different plots is showing you much, much larger plume sizes and at a different frequency. It just so happens this line you're seeing is an artifact of this plume being so bright, it actually backlit the sample holder. So that showed up on the pixel intensity analysis. Now, one of the key findings is that uh, that each of these plumes sort of had like a clustering effect, where the time between the events for at 30K would be on the order of 1 second, even though it wasn't exactly periodic, even though here at 100K it looks very periodic. But at 50K it was somewhere in between 5 to 10 second plumes that occurred, and then at 100K, where you're looking at relativistic electrons penetrating multiple grains, you see the charging build up and then give you these plumes about every 30 seconds. Of all of these plumes we saw, very rarely did we see at 100 frames per second the plume show up in 2 consecutive frames. And so while right now we don't have a well-defined velocity distribution, we know the velocity must be greater than about 1 meter per second. Some frames we did observe either the front or the tailing edge of the plume and just caught it in the preceding frame or the previous frame. And so we know these events are occurring very fast in this setup, but we don't know exactly how fast the front is on these. But certainly the higher energy electrons lead to these more intense transients through the dust field, I mean the laser field. Now the importance of this is that, well, it occurred at all temperatures. In fact, um, there was some temperature dependence that we're still looking into and analyzing, but one would expect at the lower temperature you would see the most frequent discharges, and there was a trend towards that. But even at 300 Kelvin, we still saw charging buildup on this dust and these plumes occurring. And here you can get an idea of the of sort of the frequency of these plumes. Here we have the camera's a 10-bit resolution camera, so up to 1024 bits here, and some of the most intense ones are in red, which is the 100 keV plumes that we saw were close to saturating the detector.
Need to wrap it up, Jason.
Yeah, interesting enough, looking at the witness plates, we saw these melts, and we have indication that these plumes were potentially molten when they were crossing the laser fan and left like these shadows and splats. And so we feel like there's certainly a lot of circumstantial evidence that's showing that dielectric discharge is potentially occurring, and it appears to be very distinct from the patch charge model. The ejecta is clustered, so it's not random or stochastic as you would see with hopping. And there's evidence of these melts. So work's underway to model these observations. It's really exciting work. Thank you. And I'd like to special thanks to the Radiation Effects Facility here at Goddard for their help in setting up the experiment and running it for us. Thank you.